Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a lecture on functions for intermediate algebra. This is part B, the 4 ways to represent a function. And we've already talked about domain, range, input, output variables, or independent and dependent variables. We've talked about what a function is. This section specifically, or this part specifically, we're going to really delve into 4 different ways functions are often represented. What we'll do is we'll list out those 4 ways immediately, just let the cat out of the bag, and that way we can really focus in on each of them specifically while we know about the others. I'll list them out from, I think, how they are easiest to understand to the most interesting to understand. The first way a function can be represented is via a table. To me, that's the most boring type of function just because, well, in mathematics, they tend to give you kind of boring tables. I'll try to hunt down some good tables for data for this, though. That won't be so boring. The second way a function can be represented is via a graph. The third way is via an equation. And finally, the most interesting way, in my opinion, is an application or a word problem. And that's generally how we encounter functions in the real world, is via the word problems. We'll go ahead and start with the boring table examples, just the ones that are tables that possibly represent nothing at all. Unfortunately. All right, so which of the following tables represents a function? And more than one table could represent a function, by the way. So table A, our input variable, usually when we're given a table, the input is usually the left column and the output is usually the right column. So inputs, outputs. And here we have an input of 0.08 leads to an output of 2.1, 0.10 leads to an output of 2.3, and so on and so forth. So I see, speaking in terms of domains and ranges, just if this table represented all the possible values, I know the domain, although this is not part of my question, the domain here would be the set 0.08, 0.10, 0.12, 0.14, and 0.15. I just think it's good to see every once in a while that we sneak in these concepts of domain and then range. The range is a set of possible outputs. So let's see, I have going from lowest to highest, 2.1 is a possible output, 2.3 is a possible output, 2.6 is a possible output, and 2.8 as well, and the 2.3 has already been listed. Okay. Now the question is this a function? There was no real question about writing domain and range, like I said, but it's always good to get in the habit of it. And the answer is yes, it is. The reason why it is because each input leads to its own output, leads to just one output. So if you look at all these inputs, they lead to one output. Now there is a tricky input that leads to an output here. Turns out that 0.10 leads to 2.3 and 0.15 also leads to 2.3. But the fact is 0.10 leads to one output and 0.15 leads to one output. It's okay that they share the same output. They just lead to one output each. So this is a function. Now, table B here I wrote out just because I like horizontal tables every once in a while. And if you have a horizontal table like this, typically the top is your input and the bottom is your output. Typically. Now, it depends on the situation, obviously, but almost always in a mathematical, problem, you have some. That's how it's given. So we look at this. Now, I'm just looking through my values for my inputs: 0, 1, 2, 3, 4, and 5. I don't even have a repeated input here, so I know that each of these inputs leads to its own output. Just by viewing this table, I know that's true. So this is definitely a function as well. By process of elimination, you probably have already figured that c is not a function. But let's see why c is not a function. I see the number 100 leads to 3011. The number 203 leads to 1182. The input of 501 leads to 1183. And then the input of 100 leads to 3000. But wait a second. 100 is leading both to 3011 and to 3000. So if it's like walking up to a machine and saying, if I plug in 100 to this machine, what do I get? And you can say 3011 or 3000, either one or the other. Well, once you have that option, it's not a function anymore. As another simple yet obvious example, we can take a look at a real table of data where our inputs look to be years. That's why he chose the variable y. And p would be population of the United States. And if you look through this, this is definitely a function as well, because each year leads to its own population, its own value for the population. However, there is something to be said about this. It's very difficult. You have to pretend as though you take the population sample at a millisecond. Like, in other words, 1/1/1998, January 1st, 1998, at 12:01 a.m. and 1 second, and that's it. So at least you can lock in a number. Otherwise, you can't. Some people could argue that this is not a function. So let's just pretend, for our purposes, that this is a function. In this example, we're going to start talking about graphs and seeing how they represent functions, if they do or they don't. So part A here, we have a graph, a little squiggly looking thing. And remember, the definition of a function is that each input leads to one output. So let's look at each of these, and maybe I'll choose a different color here, like black or something like that. Choose any input, like this value for an input, and see where it leads to an output. Choose this input and see where it leads to an output. And so on and so forth. Every x value or input value, I should label this x and y, every value I plug in leads to a single output. This is a function. Example B, if I choose this input, well, it doesn't lead to an output, and that's fine. It just means that we have input that doesn't lead to an output. That's okay. However, this input right here, that x value, whatever it is, when I plug in that x value, it leads to this y value, or this y value, or even this y value up here. There are three possibilities for outputs for that given input. So this is not a function. By the way, this brings up kind of a sub-theorem that I'll describe later on in a different lecture in this lecture series. However, I'll just state it right now. The theorem title is the vertical line test. It's an easy way to determine if your graph represents a function or not. The vertical line test states that a graph represents a function if any vertical line intersects the graph at most once. So in other words, any vertical line that I draw, and I could draw 1,000 of them if I wanted to, but every single one of those that I choose to draw has to hit the graph at most once. You can see every single vertical line that I'm drawing here is hitting that green curve once. Every vertical line I draw here doesn't, not all of them break the rule here. Like, I'm drawing some vertical lines. These don't hit the graph at all. However, here's a vertical line that hits the graph 3 times at least. So this immediately breaks the fact that, or our hopes that it's a function. The next example, example C here, if you start thinking about drawing vertical lines, some people might think, well, this won't pass the vertical line test because of this vertical line right here. However, there's something you should know about open holes and closed holes on a graph. If you have a closed circle on a graph, like this one right here, it means that that point exists on the graph. The open circle means that that point does not exist on that graph. So as this curve climbs up, it reaches very close to this point, but immediately hops up above. So when I draw a vertical line right here, it will intersect once, and then that's not an intersection point. The graph actually doesn't exist in that open hole. Same thing over here. I'll skip over that, draw all the way down. So any vertical line I draw hits the graph at most once. And in fact, there are some areas where it doesn't hit the graph at all. Right? And I chose to draw this example, by the way, because I wanted to illustrate the idea of domain and range again using a graph. So just to recall again, domain is the set of all allowable inputs. Well, if you look at all the x values I could plug in here, it looks to me as though I can plug in -3 as an x value because it leads to this output down here. It looks to me as though I could plug in this x value because it leads to an output up here. And I could plug in this x value because it leads to that output. And so on and so forth, all the way to x equals +3. So the domain here is a set that goes from -3 all the way up to +3, includes -3, and includes +3. On the other hand, the range is a set of all outputs based upon those inputs. So if I look at all these outputs here, let's see what's the lowest output or y value that I can attain. And if you look, I've labeled that as a height of -3. I can get all the way down to a height of -3. There's nothing, this graph doesn't actually exist below y equals -3. So there's nothing down here drawn. But now for every y value between -3 and +4 up above, I have part of the graph at that height. In other words, for +4, here's part of the graph right here. For whatever this x value is, there's a part of the graph right here. For whatever this x value is, there's a lot of the graph right there and part of the graph right there. So the range will go from the lowest possible y value to the highest possible y value. And there's no holes in the range actually, because everything, if you think about creating a shadow on the y-axis, you can see that everywhere I'm shading here, there's a point on the y for the y values of the graphs. And for every point that I'm shading on the x-axis, there's a shadow. It's a shadow from again from the graph. So these are all kind of the I guess you could say the top-down shadows, shading downward, shading downward, shading upward here, and then the reds are all the shadows going from left to right. All of these. Okay. All right. That's again a little idea about domain and range, which is not really a huge topic right now, but will be eventually. As a final example for graphs, I just want to mention most data-based graphs, so real graphs, are representative of functions. This is a crime rate for Sacramento, California by year from 1960 to 2009, and this is in millions of crimes per year. It's not really crime rate, but it's the number of crimes. So you can see like in 1970 there were actually I don't think this is Sacramento, I think this is United States crime rates. So in 1970 there was probably around 8 million crimes, and in 1991 there were about 15 million crimes. So you can see each year has a certain level of crime. So this is definitely a function as well. And by the way, any vertical line that you try to draw through this data will only hit that line or that curve once. Now we get to something that's not so easy. So we're starting to graduate to more difficult examples. And in fact, I'm going to add one on here. There we go. In each of these cases, we're going to assume that the input variable is x and the output variable is y. Right. And so if I build a table to try to figure out whether each of these is a function, it might help out, but I have to warn you, it's often a very bad idea to build a table to do anything in mathematics, because except for to notice patterns, because you often miss a lot of information with a table. But hopefully we get a little bit lucky here with our choice of tables. So I'm going to do horizontal tables for each of these problems, and maybe next time I'll use the line tool to do that. And I will go ahead and start trying to figure out what each input will lead to as far as outputs go. And to do this first one, I'm actually going to solve it for y by adding y to both sides and subtracting 12 from both sides. So I get something like that. And so I'll build some values, 0, 1. Actually, maybe I should do negative values, -2, -1, 0, 1, and 2. When x is a -2, I'll get -6 minus 12, which is -18. When x is -1, I'll get -3 minus 12, which is -15, and so on and so forth. All right. And if you look at this, each of these inputs leads to its own output. So this is a hint, although it's not a guarantee, but at least it sort of implies that this would be a function. Each input is leading to its own output. So I'm going to say that's a function. But again, I've only tested 5 values. There's an infinite number of values that I should be testing. So let's go ahead and do another table here. And this time I think I will actually draw out a line here. Nice little line. And I'll write my x, y values. Again, do all these. I'll plug in -2, -1, 0, 1, and 2. When x is a -2, I get -2 squared, which is 4, times 2, which is 8, minus 1, which is 7. Plug in a -1, I get -1 squared, which is 1, times 2 is 2, minus 1 is 1. Plug in 0, I get -1. Plug in 1, I get 1 times 2 is 2, minus 1 is 1. And plug in 2, I'll get 7, I promise. And the question is this a function? The answer is it certainly is a function, or at least it looks to be a function, even though we've only plugged in 5 points, because -2 leads to one output, the input of -1 leads to one output, and so on and so forth. It doesn't matter that some of the other inputs lead to a shared output. That's fine. It's just that I don't want -2 to lead to 2 different outputs. So this looks to be a function. Let's go ahead and do the next one here. Draw a little line in, and then go ahead and write my xy's here. And in this case, again, I'll choose C -1. I should choose -2. -2, -1, 0, 1, and 2. And because my variable x is not solved, it's been solved for, so when I plug in a value for x here, I have to start moving everything over. It might be easier for me to start solving this or start cleaning this up by solving for y. So I'm going to add 1 to both sides, divide both sides by 2, and then take the square root. And remember, when you take the square root, because it's y squared equals some junk, when you take the square root, you have to have a plus or minus. Well, first thing I'm going to note here, when you plug in a -2, -2 plus 1 is a -1 divided by 2. That's a negative number underneath the square root. So for now, I'm just going to put NR for not real. I'm okay with that. And that's still okay. It just means the graph doesn't exist right there, and I haven't broken any function rules yet. Plug in a -1, we'll have -1 plus 1, which is 0, over 2, which is still 0. Take the square root of that, that's still 0. Plug in 0, And you'll get 0 plus 1, which is 1, divided by 2, which is 1/2. Take the square root, that's the square root of 1/2, and you have plus or minus in front of it. And now I see I have an issue already. What I'm saying is, if x is 0, y could be positive square root of 1/2 or negative square root of 1/2. Once you hear that or, you know this is not a function. And again, all I did in that situation was, because I was plugging in x values, I solved this for y first. It's not always true that you have to do that. I just chose to do that in this situation. The next example is a perfect example of a situation where I don't have to actually plug in or solve for x or y to do anything. I could just use the equation that they gave me. For example, if x were a -2, well, absolute value of a number can never equal -2, so that's just, there's no possibility there. Same thing with -1. If x were 0, y would have to be 0. If x were 1, well, y could be +1 or -1, right? Because the absolute value of +1 is also 1, and the absolute value of a -1 is also 1. So you see, in this case, immediately I can see it's not a function because the input of 1 is leading to 2 possible outputs. This is not a function. The rule of thumb, although not always true, the rule of thumb is that if you have a power other than 1 on your y variable, you should be extremely careful and just double check to see if that's a function or not. If you have a function like, or a machine, I should say, I'm already using the word function because I'm starting to talk functions, but if you have a machine like the absolute value or a square root on your y variable or your output variable, you should also be very wary and check to make sure that it's a function or not by making a table. And sometimes you can just choose values wisely. Just think ahead of time what are good values to choose. Now, as an application, just a fun little thing, I just looked this up. The Empire State Building is about 1,250 feet tall. The height of a bowling ball dropped from the top of the building is given by this equation. H is equal to a -16t squared plus 1250. And so this, is it a function or not? Well, if it's not a function, that means that when you plug in a certain time, the bowling ball could be 2 different heights. Like if you plug in 3 seconds, the bowling ball could be 50 feet above the ground and 4,000 feet above the ground or something like that. That's a ridiculous statement. We already know that this has to be a function. But you can make a table of values anyway to see if it is. Well, we might as well just make a table of values. The inputs are going to be t's, the outputs are going to be h's. We'll just do a 0, 1, 2, 3. I'm not going to do negative values because we're talking number of seconds from dropping the ball, so I'm not going to talk about negative seconds here. When t is 0, h is 1250. When t is 1, we have 1 squared, which is 1, times a -16, which is a -16, plus 1250. That should be about 1234 is what I'm thinking. When t is 2, so 2 seconds in, we have t squared, which is 4, times a -16, or in other words, a -64. And then we're going to add 1250 to that. That should be 1186 maybe. I think that's about right. And then 3 seconds in, that's 9 times the -16. It's about 144, -144, sorry. And add 1250 to that. We get a height of 1,106 feet. And so you can see that this is looking to be a function, and it actually is a function. By the way, you could always, as a side note, I just want to ask this question just because I have it in front of me. When does the ball pass the 14th floor, which happens to be 147 feet off the ground? So in other words, when is the height 147? I just, for some reason, really wanted to do this. Okay, so here we have a quadratic equation I could solve by subtracting 1250 from both sides. I get a negative 1103 equals a negative 16t squared. And just make sure that's 240, 50, yeah. Okay, and then divide both sides by negative 16. You'll get t squared is equal to 1103 over 16. And then you take the square root of both sides. Remember, when you take the square root of both sides, you get a plus or minus. But this is a real situation, and the negative part of that is unimportant because we're not talking negative times here. So we're only dealing with the positive part of that. And that's roughly 8.3 seconds. So it takes about 8.3 seconds to pass the 14th floor. By the way, to hit the ground, you'd want the height to be 0. Another good question, by the way, is what the domain of this function is. I know the range is likely going to be in other words, the set of all outputs, the heights, are going to range from 0 all the way up to 1250. The times, though, will range from 0 all the way up to whenever it hits the ground. So that's something you can investigate. Finally, the most creative of the groups. So we did tables, functions represented by tables, functions represented by graphs, functions represented by equations, and now we have applications or word problems. They're not really word problems, they're just ideas or concepts. So I'm just going to list out a few things here that may or may not be represented by functions. So the inputs will be the left column, the outputs will be represented by the right column. And part A, if the input is the IQ and the output is the shoe size, is that a function? The answer really is no. I'm sure there's somebody with 100 IQ that has a size 10 shoe, but there's also his neighbor who has 100 IQ that has a size 9 shoe. And you can see right here the input of 100 leads to both a 10 and a 9. So this is not a function. And by the way, my shorthand for function is FNC. I might slip into that notation every once in a while. The second set here, the second problem, the input is a phone number in the United States with area code included, and the output would be name. Now, this is kind of a tricky one because the fact is that somebody might have or might share a phone with someone else. So if that's the case, somebody who has this number 555-555-5555, which is not a real number, but anyway, if somebody had that number, they could be sharing it with themselves and somebody else, like John and Alicia. Okay. So that's a possibility. So this cannot be a function because that phone number leads to two names. Now, if it's true that every person who has a phone number in the United States does not share their phone with anybody, then okay, this is a function. But as it's written, it's not a function. And it's kind of obvious, name leading to phone number. I don't know why people use this example, John Smith. I don't know any John Smiths, but they say it's a popular name. Anyway, there's more than one John Smith in the United States. And that name will lead to several different phone numbers, maybe 50 different phone numbers or 10 different phone numbers. So this is definitely not a function either. Now this begs the question, how many real world things are functions? Well, I suppose, there's quite a few. We really want to have functions. For example, if you're going to go down to Mexico on vacation, if you give them $10 in US, they should not say, would you like 100 pesos or 130 pesos? Once they give you that option, it's not a function. So exchange rates are functions. This is definitely going to be a function because the fact is they're not going to offer you two possibilities for a given input. So that's an idea of a function. Now I know that function changes on a daily basis because exchange rates change, but at the moment that you show up, it's not going to change. That moment that you're there, they're not going to say, "Hey, well, you got $10? I'll give you 100 or 130. Which would you prefer?" you would obviously go for the one that gives you more, but they don't give you that choice because this is a function. In our next video, we're going to talk about function notation, and that's used for equations that are represented as functions. And so when we start dealing with that section, we'll do a lot of detail with mathematical notation and computation with functions. But at this point, all we've done is really talked about what a function is, domain and range, and kind of this idea of what is a function, what's not a function, with tables, equations, graphs, and word problems. And as you can see, or concepts. And as you can see with concepts or word problems, you can kind of wiggle around and say, well, there's some times when that's not a function. There's sometimes when it is. So use some common sense and don't overthink problems, I suppose, that are presented to you.